Is Juliann Lamproe. Got it. My name is Juliann Lamproe, and I will be presenting on some neutron detection stuff. It's going to feed off of a lot of what Flynn has already shown you. I'm going to keep it kind of surface level. I don't want to go too in depth on anything because it's kind of a broad subject, but there's a textbook floating around by Noel that will be super helpful if you find anything super interesting and feel like you want to read a chapter. It's a good place to look. So to begin, just to talk about why we care about neutron detection, why do we want to detect them? There's a lot of applications, but these three are really good examples. So we use them in nuclear reactors to get our power levels as well as neutron count. And then additionally, in safeguards to measure special nuclear material to figure out the identity and sometimes the quantities of material is super helpful in well counter systems like the one shown here. And then, of course, the one that everyone finds, I think, the most interesting usually is Homeland Security. So borders, airports, things like that, keeping, things that are in, and things that are out, and making sure someone's not carrying around a handful of plutonium is always a good goal. And so I know Flynn probably talked about thermal, intermediate, and fast neutrons, but for detection, it's pretty easy to break them into just two groups. And so slow is anything below 0.5 eV, and fast is anything faster than that. And this is because the interactions, the probabilities and cross sections depend very heavily on the neutron energy. And so a lot of our detection methods are going to depend on cross sections, and they are a lot higher in this slow energy range as opposed to fast neutron ranges. And so it's important to note that all neutrons are born fast. So for example, in fission, and then are moderated and reflected naturally in the environment or purposefully for detection. And so, of course, all neutrons are neutral particles. And so we are normally detecting heavy charged particles that come from the reaction of slow neutrons or fast neutrons. And so for slow neutron detection, we're looking to detect recoil nuclei, protons, alphas, sometimes fission fragments. And then for the fast neutrons that have the lower cross sections, we are either going to moderate them to lower energies to obtain higher cross sections, or we can utilize elastic scattering to detect them as fast. And so just a refresher from the lecture that Flynn gave, these are some of the capture reactions that we're going to care about, specifically things like capture transmutation, where you are taking in a neutron's coming in, interacting, and producing an alpha and some other heavy particle. And then additionally fission, where a neutron is coming in, interacting with usually uranium, and producing fission fragments and more neutrons. And so we'll start with just regular capture-based detectors. These are neutrons are being captured by something, usually boron, lithium, or helium, and then you're producing alphas, protons, and the recoiled nuclei. And the things that are important about this interaction is that the neutron momentum is basically nothing. So your products are emitted in opposite directions, like a complete 180 of each other. And then in comparison to the Q values, so for example, this like 2.8 MeV and 2.3 MeV, the Q value is going to be much, much larger than the incoming neutron energy because these neutrons are going to be thermal. And so the energy imparted to the products or the energy shared by these two products is going to add up to be equivalent to about the Q value. And so some common capture-based detectors are the BF3 proportional tube, as well as the boron line proportional counter. And these both use the boron capture reactions to produce lithium and then an alpha. And they have these large Q values for each of the sub-reactions that are possible. And then the helium-3 proportional counter, which uses the helium reaction. And there's also lithium detectors that are usually in solid form, because there's not really a convenient way to do a gas. And the cross sections and some of the abundances are shown over here. You can see that the helium-3 has the highest cross section, while lithium's kind of lagging behind, and boron kind of aligns with helium pretty well. And as far as abundances, helium is usually the harder one to obtain. So for the BF3 proportional tube, this is just a proportional counter in which the boron is mixed with the proportional gas. So a neutron is going to come in, interact with the boron that's in the gas, and produce lithium and an alpha, which is then going to interact with the gas to cause the interaction that makes the signal in a proportional tube. And so in a perfect ideal spectrum, you're going to get these low amplitude events like gamma rays and noise down here. And then the actual neutrons are going to come in pretty distinct peaks at the Q values for each reaction. So you can see that the lower Q value is a more abundant interaction. It happens 94% of the time. But you do still get the 6% at 2.79 MeV. In actuality, there's a little bit more to the story, because you're going to get what are called wall effects, which is basically sometimes this interaction with the boron will happen closer to the edge than the alpha range or the lithium range. And so one of the products will not get to dispose of all of its energy before it exits. And so you get kind of these lingering wall effects where you either only get all of the energy from the alpha, or you only get all of the energy from the lithium and a little bit from the alpha. And it makes these kind of pretty distinct humps. And then the boron-lined proportional counter kind of takes advantage of this almost. And instead of the boron being in the gas, it is lined against the cylinder of the proportional counter. And so the interaction happens in this boron layer. A lithium atom and the alpha are produced, and the one going inward to the detector is counted, and you can see we get these kind of the opposite of the wall effects in the last detector. You get the events where the lithium is collected and the events where the alpha particle is detected instead. And so, of course, the layer thickness, increasing that is going to increase efficiency as well as self-shielding. And in this larger detector with the same amount of proportional gas in the tube is going to help your efficiency. And so, as I mentioned before, we also have lithium iodide scintillators, and so you can't get this really in a gas, so we put it in scintillators, but it works about the same. A neutron collides with lithium, and you're looking at two heavy charged particles with a very high Q value and a very high cross section at lower energies, which makes it good for slow neutron detection. And so this is good, dense material, high efficiency, and you can see that the measured spectrum examples over here, where there are minimal wall effects because of how large these detectors are in comparison. And then here's a little example spectrum or detector layout of the lithium iodide. And so another one we have are helium-3 proportional counters, very similar to the BF3 proportional counters, except instead of the proportional gas being the BF3, it is the helium gas. And these are pressurized to multiple atm, so high pressure. And then kind of the same things, except you have only one Q value in this reaction. So in a perfect world, you would only see one hump over here, but because of wall effects, we get these kind of lumpy starts where we're only seeing part of one of the particles. And again, higher diameter, but with the same pressure, you're going to minimize wall effects. And then additionally, a higher pressure just means more gas for you to interact with, and so higher efficiency. Similar to those are the fission chambers. And so it works a lot like the boron line tube, except instead of boron, you're going to have uranium. And so your slow neutrons, your thermal neutrons specifically, are going to come in and interact with uranium, cause fission. And this is going to be converted into signals to count the slow neutrons coming in. And so a lot of times these are going to be what's used in power reactors or research reactors in those types of situations. And then we can move on to the detection of fast neutrons. So we can recall from the cross-section plots that at high energies, the cross-sections kind of start to die off. It's not super probable for the fast neutrons to be captured, and that's not a great thing if we're trying to detect them. And so we can either use scatter-based detection, which I'll talk about with scintillators a little bit later on, or we can just moderate the neutrons to slow energies and detect them as slow. The important things to think about here are that eventually, if you have too much moderator, you're going to reduce efficiency. You're going to be stopping some of the neutrons before they get to the detector, so that'll make your numbers go off a little bit. But typically, a few centimeters of thickness is good. And so why do we care to detect fast neutrons? Mostly because neutrons are born fast, and so moderating adds an extra step. But additionally, with moderation, you lose some of the information on neutron energy. And so we can use these neutron energy spectrums for a couple of things to figure out what you're looking at. So if you look at the spectrum over here, you can see the difference. These are both, I think, flux or particle, number of particles versus neutron energy. So you can kind of see how the different sources change the shape versus neutron energy. You have Californium, which is just a peak. And then you have things like puby, which are a little bit more interesting of a neutron spectrum, or the plutonium oxide we have shown down here. And so a good moderation example are the Bonner spheres, which I think are some really cool looking detectors. What these do is they just add a layer or multiple layers of polyethylene spheres outside of a lithium iodide scintillator. They're most commonly used in dosimetry work, but I've seen them used in a couple other ways too. And this plot shows you the energy versus the the radius of the polyethylene sphere. So kind of going back to too much moderator can make your detector less efficient, and kind of vice versa. If you don't have enough moderator, you're not going to slow down your neutrons enough to be detected, which would also mess with your efficiency. So it's really about finding kind of what works best in each situation. And so here we talk about the helium-3 detectors. And so polyethylene moderated helium-3 detectors are a very popular neutron detector. You see them a lot out and about, but the moderation provides for high efficiency. So you're slowing down your neutrons. So we bring this plot back. You can see the difference in the fast energy range versus the slow energy range, how much more probable, a couple orders of magnitude more, 8 orders of magnitude more, it seems, you're more probable to have the interactions with the slow moderated neutrons than you are without the moderator. And so it also increases the time scale of detection to an order of microseconds. And here are some pictures of some detectors. A lot of them look exactly like this, just with a good amount of polyethylene. And then the detector cylinders are actually inside here. And so in summary, gas-based detectors like to take advantage of these reactions. The boron, lithium, and helium that I talked about before. You're looking at the heavy particles that are produced by those, so the alpha and the lithium, the recoil nuclei. And so they have high efficiencies for thermal neutrons because thermal neutrons have a lot higher cross sections, so they're a lot more probable to happen. But we can moderate fast neutrons down in energy so that they are a favorable energy to be detected in these detectors. And another thing that I didn't really talk about a whole lot is that they release a really large amount of energy. So the Q values that I mentioned are really big. Most of them are on the orders of a couple MeV, which when you're looking at comparing that to the signals caused by the gamma interactions or noise, again, it's going to be almost negligible. You'll see just that little peak that I showed at the beginning of the spectrum. And so it's really easy to tell the difference between your neutron signals and the noise that's at the very, very low energies. And so going back to the scattering that I talked about, we can use scattering for the detection of fast neutrons. So specifically elastic scattering where kinetic energy and momentum are conserved. And this is just a refresher from the slides that Flynn showed. And then this gives just a tiny bit more information. It shows you the actual schematic with everything labeled with energy and mass and the angles, and does a conservation of energy, conservation of momentum, and allows A to be this mass fraction, which simplifies things quite a bit. It makes the equation a little bit easier to use. And then we can look at that in terms of getting the max energy transferred with the head-on collision. And so in these detectors, that is what we want. We want the neutron to go in and depart all of its energy into these recoils so that we can get all of the energy collected in terms of light that are going to produce electrons and turn into a signal. And so you can see starting with just hydrogen, what's optimal for the highest energy transfer in terms of a head-on collision. And so one example of this is going to be helium-4 scintillators, which are shown here. And these are, this is just the photon comes in and it's going to Compton scatter, making electrons, and then the fast neutrons are going to come in and you're going to get your recoils, and some light will be collected and can be converted to the electrons, which then multiply and create your signal. And so it shows the difference in neutron events and gamma events over here. And I'll get into a little bit later how these different physical modes of interaction, the Compton scattering versus just the scattering to look at the recoils, will help us distinguish between the photons and neutrons, which is super helpful in applications. And so we also have organic scintillators. These are hydrocarbon-based scintillators. And so this is the neutrons are going to elastic scatter mostly off of hydrogen, which I mentioned previously was pretty optimal and can transfer the most energy with head-on collisions, so the max energy allowed. And additionally, they're low atomic number, low density. And so again, the gamma rays will, for the majority, just have Compton scattering events producing electrons, and the photoelectric absorption effect will have minimal effects. And so we have two pictures of some EJ200s, I think they both are, with some light on them so you can see them glow, which is, I think, really cool to look at. And so this is the pulse shape discrimination. So this is what I was talking about, how we can distinguish between the gammas and neutrons, because the gamma rays interact majorly through the Compton scattering. And so what we're looking at are the recoiled electrons, and the neutrons interact through these elastic scattering. And so we're looking at, when they're scattering with hydrogen, we're looking for recoiled protons. And so what this causes is in a raw signal, you can tell that there's a faster die away of the signal for the gamma ray than there is for the neutron. And so we can use an integral technique. Here it is. We can use the integral technique that looks at the integral of the total pulse versus the integral of the tail. And we can take a ratio of that to distinguish the two. So over here in this plot, we have the ratio plotted against energy. And you can see that in this lower tail to total ratio area, these are going to be your gamma rays, your smaller pulses, and then the neutrons are going to have a higher tail to total ratio, shown here with some uncertainty. And so additionally, as far as timing resolution of organic scintillators is nanoseconds. So that's really good, and no moderation allows for timing precision. So because we're measuring fast neutrons, we do not need the moderator or polyethylene that is required for the helium. Another type of measurements that we can do are time of flight, and so we can use these to get the kinetic energy of the neutrons. Basically what you're doing is you have two detectors. You have a trigger detector, which is basically just telling you when to start your count. And then you have another detector that tells you when to stop your count. And so the goal here is to measure the time between the detection at the trigger detector and the detection at the other detector. And then you have all of your other information in terms of energy and the distance between detectors. And so you can do some unfolding and figure out a lot of information through this method, along with Ph.D. and the other things that I talked about. And so here's some of the unfolding from energy gate light output. You can relate neutron energy deposition to light output. So looking at the light output from the electrons that are created and multiplied to get the signal, and you can correlate that with your energy deposition to get some information about the source of your neutrons. And so here is a little summary for the capture and scatter-based detectors. Basically, helium-3 is the conventional method. It's super common, you'll see it a lot. There's a high thermal neutron captures cross-section for the low energy neutrons, and then we can moderate down fast neutrons into that range so that they also have the higher cross sections. And this is in order of microseconds. The issue mostly is that it's expensive to produce because these gases, helium-3 and hydrogen, or helium-3 is produced from hydrogen-3 decay, which is from the weapons program, which is harder to get nowadays. So we also have the organic scintillators. So this is the scattering for fast neutrons. Issues here are low detection when you compare it with the helium-3, but they are a lot easier to get. And so we're improving precision, allows for significantly increased statistics in things like multiplicity counting, time of flight, Ph.D. stuff, some of the stuff that I showed previously. And additionally, you're looking on order of nanoseconds versus microseconds. So the time is a little better. And then just scatter-based detection summary. Anything that can be, any isotope. So elastic or inelastic scatter, but hydrogen is the better that's used because of that A factor that I showed you. It allows for more of the neutron's energy to be imparted. So yeah, the smaller the nucleus, the higher the maximum possible energy deposition. So the hydrogen that I talked about. And then organic scintillators are sensitive to both neutrons and gamma rays, but we can use Ph.D. to differentiate between the two on the fly. And organic scintillator light output response unfolding with time of flight to recover the energy information. So to backtrack a little bit and get some of the source information from the neutrons that you're detecting. And so that's all I have, but like I said, I tried to be pretty base level with things. So if you are super interested in one of those things, the book by Knoll is a really great source to look at different detection types or detector types. And then they even talk about some of the methods that I've mentioned for post-processing. So yeah, if anybody has any questions, feel free.
Yeah, thanks, Julian. Great lecture. If anybody has any questions, feel free to raise your hand in the Zoom, or you can just put a question in the chat.
Thanks for this great presentation. Just I want to ask how much we need to detector that measure the fast neutron and thermal neutron in and give the count of each of that.
I think my Wi-Fi mumbled that a little bit. Flynn, did you hear him?
Yeah, I heard most of that. Could you clarify? You were asking about the difference or something about fast neutron detection. Could you repeat that?
Just I want to ask how much we need to detector that measure the fast neutron and thermal neutron, not in just single count, but the fast neutron in the count and thermal neutron in another count. How much we need that detector?
Are you asking how large the detectors can be? For the organic scintillators, sorry, I'll just go ahead and answer this one, Julian.
Yeah, that's fine.
If you're asking about size, we're typically talking on the scale of 2 by 2 inch cylinders, or for metric system, that's 5.08 by 5.08 centimeters length and diameter. For the helium detectors, and that density stays pretty consistent between the crystals, talking about 2 to 3 grams per centimeter cubed. And then for the helium-3 gaseous detectors, you're looking at more of a diameter on centimeter scales, just a few centimeters, but a very high pressure since it's a gas. So your density is not as high as the organic scintillators, but that's where the moderation comes in to increase your efficiency with thermal neutrons. And then also the higher pressure allows for a closer density to other detectors. You have a few questions in the chat. First one, Julian, is if we moderate the incident fast neutron, are we going to lose information about its initial energy?
Yeah, I went ahead and answered that one in the chat as you were talking. But I basically just said that the neutron energy stuff is lost in capture-based systems, but it can be recovered in the scatter-based systems, so the scintillators.
I think there's another question. Oh, I think Ibrahim just wants clarification on what the mechanisms are for the moderated and the fast neutron detectors. Like the physics interactions, the type of interaction.
What do you mean? The capture-based systems rely on capture, so the neutron is captured and alpha and recoil, another nucleus are produced depending on the reaction. And in scatter, the neutron is just scattering off. And so you get the recoil nucleus and then the recoil neutron.
Yeah, and then how do we moderate for the thermal capture detectors?
Sure, that also relies on scattering. So it's the same mechanism, you're just not collecting any information from it. So things like hydrogen, you're going to be able to get your neutron to lose a lot of energy because it's it can lose the most amount of energy colliding with hydrogen. So it's going to collide with the hydrogen atom, leave some of its energy and continue on, collide with another hydrogen atom until it gets to the end of the moderator. And it will have lost some of its energy with each scatter inside of the moderator.
Thanks, Julian. We have one more in the chat. If there are any other questions, feel free to send us an email, but we'll be wrapping up this lecture shortly. But Ibrahim asks if you can elaborate on how to get the tail to total integral in the organic scintillators.
Yeah, sure. So this is actually the somewhat raw pulses. And so there are a few different ways that I know of people deciding where to start their tail integral. But total integral is, of course, relatively simple. You're just integrating this entire curve. And then once you decide, a couple of the methods that I've seen are to find this maxima. And then there is a set amount that you skip after that. So say probably like 200 or maybe 150 nanoseconds looking at this time scale. And so you'll find your max, you'll skip 150, and then you'll look at that start point all the way to the end of your peak, so about 1,000 over here. And you'll integrate that, and then you just take the ratio of those two values. So you do the integral of this smaller peak over the integral of the entire peak to get this ratio that they used for this PSD plot.
Thanks again, Julian. Great lecture. And feel free to send your praises in the chat. We'll leave it open for a minute, but we're closing the lecture for today. The recordings will be online by the end of the week. Please join us tomorrow at 1 p.m. as well for Professor Lintor's lecture on non-destructive assay. You'll learn a lot about the main applications of this neutron physics and neutron detection.
Awesome. Thanks, Flynn.
Thank you a lot.